Hi everyone, we'd like to present our paper, First Look at Private Communications in Video Games Using Visual Features. My name is Taha Ali. We are from the National University of Sciences and Technology from Pakistan, and we are very happy to be here. This is our first time. Right, a small primer on video games. It is a huge industry. There's an estimated 2.7 billion gamers worldwide, immensely popular pastime. Recent surveys show that about 60% of Americans play video games on a daily basis. Video games have immense cultural impact as well. They're bigger than Hollywood. They give rise to closely knit communities, to rich subcultures. And lately, we've even noticed that politics and activist trends have started to surface in video games. So there's an example here, which is from last year. So you might recall there were quite a few protests happening in the last year. And because of the pandemic, a lot of these protesters, a lot of people, they had virtual protests in games like The Sims, Animal Crossing, Second Life, etc. Last year, we also had the Biden-Harris presidential campaign. They purchased an island in Animal Crossing, and politicians now do uh, conduct campaigns online in video games. And it got to the point that Nintendo actually had to come out with a press release and say that please don't bring politics into the game. So the question we're specifically interested in is, can video games be used as privacy enhancing technologies? So there is quite a bit of work done on this, which goes back several decades. There are three main strategies, and these are the strategies. You encode messages in strategic moves of the game. So if Alice and Bob want to communicate via a game, they have a dictionary, both of them, and every move they make corresponds to a certain entry in the dictionary, which decodes into certain useful information. So that's been demonstrated for several games. Covert channels have been demonstrated in Quake 3 Arena and in Zero AD. Steganography has been demonstrated for Solitaire, Pac-Man, Pong, Tetris, Team Fortress 2. So you hide your message in the actual data communications of the game itself. Now, what these works have in common is that generally they require game clients to be customized. They require the exchanging of dictionaries for certain cases. Users have to be relatively sophisticated. These channels have typically very low bandwidth, so they're recommended to maybe bootstrap secure communications somewhere else, or for microblogging, for Twitter style messages, for public posts, that kind of thing. The threat model is common in the sense that the channel or the dictionary, that itself is the secret. Once that is revealed, everything else is out in the open. So the aspect we intend to explore is, can we communicate using visual features in the game? So as you might be aware, games are becoming more immersive now, and you have greater flexibility in manipulating the environment. So can you use that? And can you specifically do that in such a way to evade automated detection? Because text spotting in the wild is recognized to be an open and challenging problem. So we believe we're the first to look at video games from this particular perspective. So here's how it would work. If Alice and Bob want to communicate, let's say in Grand Theft Auto 5, that's an action adventure game. Alice picks up a gun and she finds a surface and she fires her message on the wall, right? I think, therefore I am. If it's a strategy game like, let's say, Clash of Clans, where you have to arrange structures or buildings, you can do that to spell out your word or your message, hello world, in this case. Now, again, this can be used to bootstrap communication channels, to share links for Tor bridges, for microblogging, digital graffiti. And that's actually a very relevant example. If you look at this, this is graffiti which was witnessed in Istanbul in 2014 on several walls. In 2014, for the general presidential elections, the Turkish government banned Twitter. And users soon discovered that it was a very simple DNS block. And you might recognize the IP address here. This is the IP address of Google's DNS servers. So once people entered this information onto their computers, then they could access Twitter all over again. So something like this could easily be done in a game. And it took us about 5 to 10 minutes to do something like this. This is in Grand Theft Auto 5. Right. So our contributions are, in our paper, we demonstrate that state-of-the-art text spotting tools fail to detect text in popular games. And we explain why. And then we retrain these tools for specific environments, for these particular environments. And we show that performance improves, but in very limited ways. And we demonstrate techniques which can defeat tools that have been retrained. So these rely on inherent design limitations of these tools, of text spotting technology. And in our paper, we also propose certain mechanisms to improve efficiency, security, and bandwidth. So a quick primer on text spotting. Text spotting in the wild is recognized as a challenging problem, like I mentioned, by the computer vision community. The reason is that unlike text spotting in other environments, like let's say documents, a document is very orderly, it is very uniform, the background is white, there's only text, it's very structured. But in the wild, things are not that straightforward. There can be lots of background objects, there can be a lot of clutter. The fonts can be written in strange ways. The fonts can have lots of curves. Lighting makes a difference. Perspective, especially, it warps the geometry of the scene, what is being seen. So if you look at text from a particular perspective, it can be much, much harder to recognize. So we use 4 state-of-the-art text spotting tools for our work here. So 2 of these, the first 2, Deep Text Spotter and ABCNet, are from the academic literature. They are the leading tools. And the other 2 tools are proprietary tools, Google Cloud Vision, Azure Cloud Vision. They are online services. There's very little literature about them available. But all 4 of these tools are recognized for extremely good performance on benchmark data sets. So they are acknowledged by the computer vision community to be state-of-the-art. And this is how they work. So this is native text within the game, Grand Theft Auto 5. Native text is text which is already there. We did not put this text, it was already there in the game. And when you run the tools over it, these text spotting tools, so you can see that they've accurately identified they've localized the text in the bounding box, the red bounding box, and they've also highlighted what the word actually is. So these tools are extremely effective for text spotting in the wild. Now, for our experiments, we had to come up with an all-new data set because there's no such data set of text generated in games. We modeled our data set on the Street View text data set, which is a classic data set in the vision community. Our data set is actually, we've released it, it's released to the public. We've shared a GitHub link in the paper. The original Street View text had Street View images with signs on billboards and signages, and everything was labeled. So it had 350 images, 904 words, about 2047 characters. So we replicated this data set for three different games. And we also, for controls purposes, we also included 50 images of native text from within games, 50 images of arbitrary shaped text with fancy fonts, different types of curves. And we took images from different perspectives, 3 different perspectives for each word. And it took 6 students approximately 250 hours to do this over 2 months. So this is, again, the effort it took us was immense because unlike a normal data set where you just take pictures and you label them, we had to go into the games and actually physically generate these words. And it takes about 10 to 20 seconds to generate a single character, not a word, a character. So it took us a lot of time to do this. And these are the games, Grand Theft Auto 5, Call of Duty 4, and Minecraft. 2 of them, Grand Theft Auto 5 and Call of Duty 4, are similar. Minecraft is a completely different genre. And overall, so these are the most popular games in the world right now. They regularly clock in about over a couple of 100 million users on a monthly basis. And this is this is just to give you a flavor of the data set. So in the first column, if you look, you've got the Street View text original images, you've got Target and Murphy written down. And we recreate Target and Murphy in the second column for GTA 5, Grand Theft Auto 5, for Call of Duty, and for Minecraft in the very last column. These are the results of the tools. So when we run this on the data set, you'll observe in the second, third, and fourth column that performance is pretty poor. For Deep Text Spotter and ABCNet, it clocks in at 0. They don't recognize any of the text. Azure Cloud Vision, the last row, is less than 1%. Google Cloud Vision does better. It goes up to almost 6% for the case of Minecraft, but otherwise the performance is still negligible. But on the other hand, if you look at the last 2 columns, the native text within Grand Theft Auto 5 performance is pretty good. It goes up to 85.6% for Azure Cloud Vision. And for the very last column, on the original SPT data set, Azure Cloud Vision goes up to 91.8%. It recognizes most of the words, almost all the words. So what we're seeing is that these text spotting tools, they do work in the wild, as you can see in the last column. They do work on text which is actually already in the game, which is the second last column, but they fail to recognize text which we generate in the games ourselves. What could be the reason for that? So here we attempted an explanation from the computer vision literature. So this is what a standard font looks like, standard piece of text. So you've got two properties which stand out, a continuous boundary and a uniform structure, homogeneous strokes. Now, when you break up the boundaries, when you come up with discontinuous boundary, this is called an LED font. You might have seen it in billboards and in signage. When you break up the boundaries, when you have discontinuous boundaries, this is recognized to be a problem because now the search space to find the right character, that increases significantly. And when we push it one step further, when we come up with a non-homogeneous structure, as we do with the case of bullets, then it becomes extremely challenging because now it's not entirely clear to the tool which component or which part of this picture is part of the background and which is part of the actual text. And how does it all fit together? So that is why our performance for these tools is so poor. So we retrain these tools for, we've got the pipelines for Deep Text Spotter and ABCNet are open source, so we can retrain these tools entirely for these games. And we notice that Deep Text Spotter improves marginally. It goes up to between 6 and 7%. ABCNet improves significantly. It goes up to 64.67%. And the reason for this, we believe, is because ABCNet is specifically designed to accommodate a slight amount of curvature in the text. And we look at one other interesting result from here, which is that we try to see can these results be generalized? I mean, can I retrain a tool for one game and use it to detect text in another game? How would that work? What kind of result will I get? So here, as you can see, for the case of Call of Duty 4, if you retrain ABCNet, performance improves to 42%. But when you use that same tool in GTA 5, the performance is between 10 and 20%. Likewise, for GTA 5, if I retrain ABCNet, I go up to 64.67%. But when I use that same tool, a retrain tool on Call of Duty 4, performance is between 10 and 20%. So the benefit is marginal, it's not that significant. And none of these results generalize to Minecraft, because Minecraft is a completely different type of game with different textures, perspectives, and materials. And another problem that we see is that all of these detectors fail when you generate arbitrary shaped text, when you have a significant amount of curvature in the text. So we can read this text fairly easily, but all four detectors retrained, the two detectors that we've retrained, all of them fail to recognize this text, because this is an inherent design limitation of text spotting technology, that it cannot handle a large amount of curves. A quick word on adversarial capabilities here. So we're nearing the end. So what we have here is the standard prisoner warden scenario. That's the threat model that we have, where Alice could be in prison who wants to communicate with Bob on the outside. And Eve, in our case, is the warden who is inspecting all messages that go from Alice to Bob. And in our case, Eve is automated because video game traffic is fairly significant. It's one of the largest components of internet traffic as a whole. So it's not possible for humans to surveil all of it. But in this case, our warden could be a hacker, it could be a network administrator working for an organization or a company. She could be someone working for a gaming company like maybe Nintendo, who wants to see what kind of communications are happening between players. Or she could even be working for an intelligence agency. Now, what we've seen so far is that these automated tools, they fail out of the box. They do not recognize any of the text. You can retrain them, but that has high costs and effort, and the benefits are very limited. They don't generalize much, and they can still be defeated by arbitrary shaped text. So many of our adversarial models actually might not have the resources to undertake this exercise. Like a normal network administrator or a hacker cannot do the whole. It would be quite a bit of effort to do the whole retraining exercise, or for a game company. But when we come to the intelligence agency model, things become very interesting, because These agencies have incredible resources. They can come up with huge data sets. Our data set was between 3 to 4,000 images. They could easily come up with data sets of tens of thousands, even hundreds of thousands of images. And they could even come up with, they could even push the state of the art in terms of technology. They could come up with text spotting tools which can handle curvature. So that's entirely possible. And there is a slight precedence for something like this. So this is a news item from the Snowden leaks, which was about, and this news item came on about 7, 8 years ago. The NSA actually spied on World of Warcraft and Xbox Online games, and GCHQ actually went to the extent of designing customized tools to parse traffic for World of Warcraft and to access the voice communications of players. So something like this could be done, and there has been such activity in the past. And if these entities do have these types of resources, they could even go one step further. They could skip automated tools entirely, and they could just put human agents in the game, because human agents can see this and can recognize this kind of text. And again, we have a precedence in the Snowden leaks. Uh, the NSA actually infiltrated World of Warcraft. And it's actually very interesting because it's not just the NSA, GCHQ, the FBI, the CIA, and one or two other such agencies, they all sent agents into games because they were convinced that there might be terrorist communications happening inside games. And then it got to the point that the agents were tripping on each other's feet. And then they had to set up a special committee to sort of harmonize the operation so that they don't sabotage each other's intelligence activities. So this could be done. So this is a new area. The way we see it, our work is sort of a first step. There's a lot more work that needs to be done. We need more data. We need more tools. We need more experiments. We need more input from the computer vision community on what can be done and cannot be done in this domain. What we're working on so far is we're trying to improve the usability of this technique. We're trying to automate it so that it's not so painstaking to type in the words. I'll leave you with just just a comment for food for thought. So future trends, what we're seeing is text spotting tools are improving. Every year, if you go to CVPR, you find a new tool which has extremely good performance. But at the same time, video games are also improving. They're becoming even more immersive, and you're getting greater flexibility and greater control over the environment, how you can manipulate objects and what you can do. So which way things will swing, how this cat and mouse game will go, that remains to be seen. So that's pretty much it. If you find this topic interesting, there's a lot more work in our paper. There's a lot more results we couldn't fit in because of time constraints. We are happy to take questions. That is it for now from our end. Thank you for listening. Thank you for your time. Take care. Bye.